Right, I'm going to talk to you today about Unit 4 from the Senior Physics. The first topic is special relativity, Einstein's theory of relativity, or special relativity. Now, he formulated that in about 1905. Up until then, they had a different view of the way the world went in terms of time and space and things like that. Einstein came along, and he was one of the first people to give a new idea about how time was, and time wasn't a fixed thing like it was thought in Newtonian times. So what I'm going to do is break this section. This will be chapter 9.1a from your textbook. Now this is the text, of course, that I'm using. 9.1, I've broken it up into three parts, A, B and C. So I'm going to do A first, and then I'll do B and C as separate videos. Now the thing we're going to look at in this one is what's called the problem of muon decay. Now muons are tiny particles, subatomic particles that are created in the Earth's upper atmosphere. So can you imagine protons coming from the sun? Now the sun gives off this solar radiation which consists of a lot of protons. Now those protons hit nitrogen molecules in the upper atmosphere, maybe 30 kilometres up, and they turn into these things called pions, P-I-O-N-S. Now pions are just quarks and antiquarks together. Now you'll learn about that in chapter 14. So these pions, which have the symbol pi, are just a particle made up of a quark and an antiquark. Now those pions decay into things called muons, M-U-O-N-S. Now they have the symbol mu, which is the Greek M, the mu. Now they can be positive or negative. They're like electrons. They're very much the same as electrons. They have the same charge as electrons, but they're much heavier. So you can think of them as heavyweight electrons. So these electrons, let's treat them. We'll look at the negative ones. Now those muons decay into, basically into electrons, and you get a few other things like neutrinos and so on, like you learnt in chapter 6, I think it was, when we did nuclear decay. Now the time from the muons being created until the muons decay, that time there is about 2.2 microseconds. Now that's micro. It's the same symbol as the muon, but it's just a micro symbol, and that's 10 to the negative 6. So as far as the muons are concerned, they last about 2.2 microseconds before they break into this stuff here. Now that's the average time. Now if that was a muon travelling along, so imagine a muon travelling along, it would last on average 2.2 microseconds before it decayed into these things. Now some of them will last longer than that, others will be a shorter time than that. Now you could get some that are about a quarter of that, so a quarter of that might be, say, 0.5 microseconds, and you might get some that are about 4 times that, so that's about 8.8 microseconds. The average is about 2.2. Now that's called the rest lifetime, because that's the time that a muon would see itself as lasting before it decayed. So here's my muon. It'll be travelling along, and after 0.5 of a microsecond, some will have decayed, but the majority of them, the average, will decay after about 2.2, but some will last 8.8. So that's the lifetime in the what we call the frame of reference. In other words, the as measured by the someone travelling along with the muon itself. So if you had a muon and you had a stopwatch with it, you'd measure it as you travelled along with it. You'd measure it as being 2.2 microseconds on the stopwatch. Now that's called the time, but we put a little zero after it to indicate that, well, in some ways, to indicate that it's measured, the time is measured by someone who's travelling at 0 meters per second with respect to the muon. So you're travelling along with the muon as it goes down. Okay. Now what happens is There's an experiment done in about 1964 which was using this information, but it tended to support the idea of, or the what will I say, the outcomes of the special theory of relativity. Okay, so let's have a look at how this will work. So just keep in mind the rest life, T0 for a muon is about 2.2 microseconds, but it could be less, that some will be less and some will be more. Okay, now the experiment done in 1964 was over at a place called Mount Washington. Now let's imagine that's the mountain. This is Mount Washington. Now it's about, if you measure the height, it's about 1910 meters. Now that mountain is in New Hampshire in United States. It's about a 2-hour drive north, sort of northwest of Boston, and there's a laboratory at the top. Now it's not a steep mountain like that, it's more curved, but just for the purposes of this I'm showing you it like that. And there's a laboratory at the bottom. So they've got 2 laboratories that can detect muons. So as these muons are created up here, so these are the muons. So as they're created, they pass through this detector here. Okay, and that will count how many there are in an hour. Now, in the experiment done in 1964, they reported on the results they had. Now, I looked up the original paper, and there was something like 540 per hour. Look, I'll call it 540 per hour to the -1. Now, when they measured the number down the bottom here, they expected that based on how fast they decay, they'd get none. They thought they should get about 29 per hour at the bottom. Okay, so based on how many should be left, because a lot of them would decay as they went through, there should be 29 per hour. But what they were getting was something like, I forget the exact numbers, but it's about 450 per hour. So they were getting a lot more than they calculated. Now the reason for this fits in with Einstein's theory of relativity. What we have to do is look at the speeds of these and how long they'd last. Now these muons travel at about 995, let's call it that, C. So that's 99.54% of the speed of light. Now you know the speed of light is 3 by 10 to the 8. That was from chapter 6 or somewhere back there. So V is 0.9954 by 3 by 10 to the 8 meters per second. Now that comes out pretty close to 3 by 10 to the 8. Now this is really 3.00. Even though in the formula book it says 3, it's closer to, well, it's actually 3.00. But we just use one significant figure in the formula book. Now that comes out to about 2.996, I think, or something like that, by 10 to the 8 meters per second. The main thing is it's travelling almost at the speed of light. Now if you had to work out how far these things would go in that half-life time of 2.2 microseconds, you'd use this. V equals S on T, so S equals VT. Okay, let's work out S for this. The V is 2.996 by 10 to the 8 times the time. Now the time is 2.2 by 10 to the negative 6 seconds. Okay, that's the 2.2 microseconds. Now if you multiply all that out, that's about 3 times 2.2. It comes to about 660 meters. Okay, if you see that, the 8 minus 6 comes to 2. Get rid of that. And 2.2 times 3 is 6.6 by the 10 to the 2, which is 100. So it's 660 meters. Now that's how long they should have lasted. So in other words, the average. So 660 metres, if this is 1900, 660 metres would be something in there. So these muons should have all decayed, or most of them should have decayed by the time they were there. And that's why they only expected 29 at the bottom. A few of the longer living ones would have made it. But in fact they found 450. So how do we account for that? Well, it's pretty straightforward. Now just think, I'll leave that as 660 as the typical distance that they should travel. But let's have a look. I'll just remove all this now. We don't need that. Now, as far as the particles are concerned, if you are travelling along with the particles, they should last 2.2 microseconds. So if you were a muon, by the time you got to about here, you'd be ready to decay. But the scientists were noting most of them were still present down here. So in fact, what it appeared was that the lifetime, the rest life of these muons, wasn't 2.2 microseconds. That's what it was to the muon itself. But to a scientist, to get this number down here of 450 or something like that, these muons must have been lasting about 23 microseconds. So what was 2.2 microseconds to a muon was to the scientists observing the muons was 23 microseconds. Now this was T0 because that was the time as measured by an observer travelling along with the muon. In other words, the observer had 0 meters per second speed because they were travelling along with it. They were riding on the muon, if you like. This is now called T, just ordinary T with no subscripts. So we've got T0 and T. Now, Einstein's formula can allow for that. If you set up a formula with that as the speed of the muon, this is the rest lifetime of the muon, you can actually work out the time that the observers would see. Now this is a bigger time, so that's bigger. Now the word we use for bigger is dilated. So this is called the dilated time interval. Now interval because it's from birth to death basically. Now the di part means, it comes from the word, the Latin word dis, meaning apart, such as in dissect. When you dissect something you take it apart. So that means apart, and this part here, lato, L-A-T-U-S, means wide or something like that. Okay, such as in, what words do you use? Population, that's a wide group of people. There's probably other words that you'd use. We've talked about dilate. Anyway, there's other words with latus in it that would mean wide. So this is something that's been wide apart. So the time has been spread wide apart from 2.2 to 23. So that's called the dilated time interval. Okay, so that explains it in terms of the way the scientists see it. The scientists are seeing it as 23 microseconds. So of course there'll be a lot more that get to the ground. Now let's have a look from the viewpoint of the muon itself. Now as far as the muon's concerned, it only lasts 2.2 microseconds. Now it knows it's travelling, and I know it doesn't know, but an observer travelling along with the muon would measure a speed relative to the mountain of 0.9954 c. Okay, and it would know that it should on average break up after 2.2 microseconds, which would put it about here. But it's not doing that. Okay, so as far as the muon is concerned, something is different about this mountain that allows them to get to the bottom before they break up. So what the muon sees is this whole mountain is being squashed up. So that mountain, instead of being 1910 meters, to a muon appears to only be about Now I've got the exact values in the book. I think it's about 180 metres. Okay, so the muon sees the distance, the height of the mountain as being contracted. So this is called length contraction. Now, okay, so the length, or the height in other words, the height of the mountain is being contracted down to 180 metres or so in the frame of reference of the muon. Now the scientists measure it as 1910. The muon measures it as 180. Now what happens is the person measuring this mountain is at rest with respect to the mountain. So the scientists, be it on the ground, they'd measure the height of it. Now you could imagine if they had a ruler, I haven't got one here, but they could take a ruler and measure the height, or a tape measure the height. Now they'd use other methods, but that's the measure. That height is the height as measured by a person who's at rest with respect to the distance. Okay, so this distance here is L for length, but because the person measuring it was at rest with respect to the mountain, we call it L0, because it's zero speed with respect to the thing being measured. Now this would be called just plain old L. That's the contracted length. Now sometimes this L0, which is 1910 metres, is called the proper length, but it's still it's a contracted length. So you'll often see it in the textbook as proper length, contracted length, or even relativistic length, because it fits in with Einstein's theory of relativity. Now there is a separate formula that relates L0 and L and that speed. Now I'm not going to give it to you here because the length contraction one comes up in a later chapter. In fact, it's in chapter 10. This is chapter 9. In chapter 10 we do length. In chapter 9.3, I think, 9.3, which is I'll come to soon, we do the time dilation, the lengthening of the time. Now the formula used for the time is similar to the formula used for the length, in that it takes into account the speed, the rest time, or the rest lifetime, and what I said before was the dilated time, T. It also, there is a separate formula that uses L0, L, and the speed. The two formulas look almost the same, but you'll see them as we go through the other chapters. Now, I might leave it there. I'm going to just mention a couple of things before we move on. In the next video I'm going to look at something to do with these frames of reference. You've heard me talk about frames of reference, so I'm going to do frames of reference, and then also that'll be 9.1 part B. Now it's not called part B in the text, it's just the next page. And then part C, which is on page 249, be 250, I'm going to look at the postulates of special relativity. So it'll look at how time and space changes, or basically the speed of light and the sorts of experiments you can do under Einstein's theory of relativity. Just before I finish this video, the question will come up, how much of this do we have to know? Now I've been through a lot here, and you might think, what do we need to know in terms of all of this stuff? Now on the test, on the external exam, you're bound to get a question on the muon experiment. It's one of the key points of special relativity, key confirming points. Now you could either get a multi-choice or a short answer. If it's a short answer, I'd suspect it'd only be 2 marks, because really you're just recounting, you're describing the experiment. Probably 2 marks. If it's multi-choice, well, there'd only be 1 multi-choice question on the paper. Now let me just tell you what the 2-mark external exam question could look like. Now I've written this up as CYL 9.1 question 1. So if you look on a few pages in the text, I've basically got what I would expect a exam question would be, a external exam question would be. Now I would imagine it would look like this. Okay, I'll just go through that again. I imagine it'd look like this. They'd say, describe how the muon experiment supported the idea of relativity, or of special relativity. Now what you'd do, you'd have to go through a couple of things here. Now you wouldn't want to go into too much depth, because the description part doesn't really need calculations. Well, you'll get calculations on this in the separate section of the text. What you'd say would be something like, the muon experiment confirmed Einstein's theory of relativity, because the number of particles at the top of the number of muons present at the top of the mountain would have indicated how many there should be at the bottom, but there were far more at the bottom than they would have accounted for. And that's when I went from 500 and something. There should have only been 29, but there were 440. So the number of muons at the bottom of the mountain were more than the normal sort of calculations would have allowed for. Now you'd have to word it something like that, without going into too much more detail. You might put in a little bit of supporting evidence, but I think once we've done the later sections, you'll be able to flesh that question out a bit more. Now as far as multi-choice questions go, what they'll do is they'll try and trap you. What they'll do is they'll say, which of the following is the main feature of the muon experiment for special relativity confirming? No, they'll probably just say, what's the main feature of the muon experiment related to special relativity? One of them will say, the right one, the correct answer, will say there were far more muons present at ground level than were expected based on the number there were at the top of the mountain. Now that's probably all they'll have as the option. Now that'd be the most correct. What they'll also have are some some options that are true, but they are not exactly right. They're not what confirms relativity. What they'll say are things like, the half-life of a muon is 2.2 microseconds. Now you might see that and think, yeah, that's true, but that's true, but it's irrelevant. Well, it's relevant, but it's not the answer you're after. Or it might say muons are created in the upper atmosphere, or the experiment was done at Mount Washington, which is 1910 meters high. So they'll have some facts, some true statements, but that don't really support the idea of relativity. The only one that supports it is there were more muons at the ground level than would have been calculated by the old Newtonian formulas, the V equals S on T and so on. So that'd be your answer for that. Now I'm going to stop there. The next one I'm going to talk about is frames of reference, but that'll be the next video. So we'll leave it there.